All right, recap lecture number 4. We are going to be talking about Riemann sums, talking about rectangles, but also a little bit of trapezoids to estimate the area underneath a curve, which we know that if we had an infinite number of rectangles, what we really would be finding would be the exact area from A to B underneath some curve. But for us, we are going to do some Riemann estimations to get there. So to start, we have the right-hand rule, and I'm going to choose to use 4 rectangles. So I'm going to take B minus A, 4 minus 0, divided by 4 rectangles. So each one is going to have a partition width of 1. And I'm going to look at this partition in particular, and I'm going to say, okay, here's my right hand. That's going to create the height of that rectangle. Then I'm going to look at this partition. Here's my right hand. That's going to create the height of that rectangle, the height of that rectangle, and finally this short little rectangle over here. So we can see that we have our right hand rule done. Next then I'm going to think about a left hand rule. So again I'm going to partition with 4 rectangles. So 4 minus 0 divided by 4 is going to partition into rectangles with a width of 1. Although this time I'm going to use my left hand to create the height of the given rectangle based off of the function. Board is not calibrated the greatest over here, but trying to get the point across. This one should maybe be just a smidge lower. Okay, so we have our left-hand rule for our estimations. Now, if you think about increasing versus decreasing, you can tell if your approximations are going to be over or under. I don't think it's worth taking the time to learn hard and fast rules, but just sketch a quick little curve and you'll see pretty quickly how those estimations are coming out. So right hand and left hand rules are all well and good, but a midpoint estimation is going to give us just a little bit better approximation for that integral we're looking for. So I'm still going to take my bounds, 4 minus 0, and divide them into equal partitions of 1. But instead of choosing the left or the right of the partition, I'm instead going to choose the midpoint. So I'm going to use that height of the function to create the height of that Riemann rectangle. So here's the middle between 1 and 2, and the height at 1.5. Here's the middle between 2 and 3, the height at 2.5, and then the middle here. So I have this rectangle, this rectangle, this rectangle, and this one. And you'll notice that the midpoint helps us approximate a little bit better because for every little smidge that I'm missing, I'm gaining on the other end. Finally, then we have the trapezoid rule. And yes, there is an official formula for the trapezoid rule involving using base 1 only once, but base 2 twice, and then the last base only once. But if you don't want to memorize a rule, again, you can just find trapezoids individually. So I'm going to use 4 trapezoids just to keep our numbers nice. So I'm going to draw this height and this height, connect them poorly in a trapezoid. Use this height and this height, connect them in a trapezoid, this height and this height, this trapezoid, and a trapezoid. The area of a trapezoid is 1/2 base 1 plus base 2 times the height. In this case, all of our trapezoids have the same height of 1. This would be a base and a base. So B1, B2, B2, B3, 3, B4, B4, B5. So you can think about how that could create a nice trapezoid rule for us if we had even partitions of H every single time. Fortunately though, AP does not always give you nice equal partitions as far as your trapezoids are concerned, which is why it's important to just know how to work in trapezoids in general. So what we have here is a chart of values. We've got our x's and our y's, and we are looking to estimate the area underneath the curve from 0 to 10 of this function. So ideally, we would like to use an infinite number of rectangles, or, well, trapezoids too, right? Rectangles would get us until they are infinitesimally small, which really you would just be summing up lines, and you get your nice two-dimensional area from geometry. In this case, though, we don't have enough information to know our exact curve and to use our calculus rules. Instead, we're going to use some Riemann estimations. So, Try to think if you can find the left-hand estimate, the right-hand estimate, and the trapezoid estimate. You are going to pause your video and check in just a couple minutes. All right, checking over your answers, you should see that your left-hand estimate should come out as 35 and your right-hand estimate should come out as 38. What I drew up on the board is thinking about our widths of our partitions. We have one that's 2 and then 3 and then 2 and then 3. So if we think about each rectangle individually for the left-hand estimate, we're going to use a width of 2 and then the left hand of 1, then a width of 3, left hand of 4, width of 2, left hand of 6, width of 3, left hand of 3, and that gets us our 35. Whereas for the right hand rule, we are going to use our width of 2 and then a right hand of 4, 6, 3, and 2, right? Now, some people like to sketch a picture. That's totally fine too. We've got 0, 1, we have 2, 4, we have 5, 6, 3, no, sorry, 7, 3, and we have 2, 10, 2, just somewhere between there. But you can sketch it out like that if that helps you to draw out your rectangles as well. Then for your trapezoid rule, again, you notice that the heights change, 2, 3, 2, 3. So you cannot use just a trapezoid rule. You need to actually do a trapezoid estimate, thinking about 4 separate trapezoids that you can use for a total of 36.5 as our area estimate. All right, the next thing we have to talk about then are the mean value theorems. We're going to focus on integrals because we're just talking about Riemann sums, but we are going to touch on the mean value theorem for derivatives. So mean indicates that we are talking about some sort of an average. When we talk about the mean value theorem for derivatives, we are saying the average part would be the slope of the secant, which is going to be f of b minus f of a over b minus a, or old school slope, is equal to our instantaneous rate of change for the derivative. All right, so we've got average being equal to instantaneous. All right, well then, if we think about the mean value theorem for integrals, we are going to talk about the average height of a rectangle. Okay, the height of that special box, that's going to be equal to our exact area underneath the curve. So officially, we are talking about, I'll write this the way that we usually see it, the integral from a to b of f of x dx is equal to b minus a times f of c. So in this case, this is the exact area under f of x is equal to the average height times b minus a. So this is the part that the average shows up, just like this is the part that the average shows up. Right? So again, we're talking about f of c being the height of the special box, which will be drawn in red in just a second. Alright, so thinking about a sketch. Thinking about a sketch, okay, we're not going to write it, we're going to draw it, okay, of our theorem. If I create some function, call this f of x, we're going to say this is a, this is b, okay. If I wanted to find this area underneath the curve, I know that I would have the integral from a to b of f of x dx. That finds that yellow area, or the area underneath the green curve. But what the mean value theorem tells us is that there's somewhere along here, if I let this be the width of one rectangle, okay, there's some height along in here I don't know exactly where it is. To be honest, if you have multiple ones, right? But I'm going to choose this one. I think this seems reasonable. We'll talk about how to find it exactly in just a little bit. Where the area of this red box, which has a height of f of c, right? The area of this red box matches the area underneath the yellow. So I'm missing area here and here and here, right, from the green one, but I'm gaining it with the red one. You gotta think about that in terms of average. So this is gonna be equal to b minus a times whatever the height of that box is. Right? Area of a rectangle, the base times the height. So there's our f of c, or our special height that's coming into play. You might remember these pictures from when we first learned the MBT. Now, the mean value theorem for integrals can be rearranged slightly. So we know this was true from the previous slide. As if the special height doesn't necessarily mean it's half between the heights, right? It's a special height that we can find. We can find this value of c, which we can do in just a minute. But we can also rearrange the MBT into average value. We do that by just dividing out this b minus a. So to find that special average height, right, that special height, you can use the average value formula. All right, something to think about really, really quickly is how this average value relates to average rate of change. So average value, if I wanted the average value of f, f goes in the integral. If I wanted the average rate of change, I would want to find the average slope, or old school slope. Okay, so average value, that goes in the integral. Average rate of change, that function f goes in the top part of your old school slope. Think about those two concepts separately. Alright, so I want you to go ahead and pause your video and try the next two problems on your own, and then we'll talk about them. Alright, due to my free recording software, I am going to need to make a second video for the other two examples. I apologize for that. But just to talk about this one real quick, so we want to find the special c. So we're going to start by setting up our MBT for integrals, right? And you're going to integrate this 9x to the negative third, hold out the 9 in front, okay? And divide it by the 2 that was over here. So we know that this whole thing is equal to 9 over c to the third, because f of c, if you plug c in for x, you get 9 over c to the third. So going through, integrating, we get this lovely integral that is all ending up being equal to 2. That is still equal to 9 over c to the third. So to solve for c, we end up with the cube root of 9 halves. Your final answer. Okay? This one, same thing, you want to start by setting up your full average value. So pi over 2 minus 0, sorry, not average value here, MBT, times f of c equals the integral from 0 to pi over 2 cosine of x dx. Isolating f of c, you end up with f of c being equal to 2 over pi. So if I wanted to know the exact c value, I would take the cosine inverse of f of c. Cosine of c equals 2 over pi, which means that cosine inverse of 2 over pi, and I don't have a calculator handy while I'm recording, is going to be equal to c. Alright, so we're going to conclude this video, and we're going to talk a little bit more with integrals on the next